So, hello everybody to the session on scalable data science, which is a new session overall at VLDB to talk about and learn about research in areas of data science and involving massive data. And we have several invited talks here. So this is an invited talk session with two excellent speakers, and I'm very happy about this. And we have this session being chaired by myself. I'm Volker Markel from TU Berlin, as well as from Angela Bonifati from Lyon, who is online. And the session's first speaker will be introduced by Angela.
Hello, everyone, and welcome to the Scalable Data Science session. As Volker said, this is a novel session at VLDB, and there are exciting talks. So it's my pleasure to introduce the first talk by Joaquin Vanschoren. The title of the talk is Towards Scalable Online Machine Learning Collaborations with OpenML. Joaquin is an assistant professor at TU Eindhoven, the Netherlands, and his research focuses on machine learning and artificial intelligence, and in particular on automated machine learning and meta learning. He has co-authored and co-edited books on this topic and published over 100 articles on these topics, and received also many related grants and awards. He also has founded openml.org, which is an open science platform for machine learning. Maybe many of you have experienced that, and is a founding member of two European associations that are well known in this field, ELIS and CLAIRE. He also chairs the Open Machine Learning Foundation and co-chairs the W3C Machine Learning Schema Community Group. He has been tutorial speaker at many conferences, New RIPS and AAAI, and has given more than 20 invited talks at various conferences and workshops. And I think we are very lucky today to have Joaquin as an invited speaker at the Scalable Data Science session at VLDB. So welcome, Joaquin, and looking forward to your talk.
Thank you so much for that very nice introduction. I'm very happy and also very lucky to be here. And I hope we have some interesting discussions today. I'll start with sharing my screen. All right. Good. I hope you have the right view. No. That's better. Okay, cool. Thanks, everybody, for joining. So I'll talk about OpenML and how we plan to use it to make machine learning collaborations really scalable worldwide. This is a talk by me, and definitely also by the whole other, the rest of the OpenML team, which I will come back to introducing. So first, let me take you to the United States, to the deep mountains of New Mexico. So there's a telescope complex there. It's called it's part of the SDSS, the Sloan Digital Sky Survey. And so it's an amazing project that really makes astronomy massively scalable. So inside this white box here is a telescope. And what it does, basically, it does nothing else than mapping the entire universe. It's a robotic telescope. So every night it scans part of the universe, and it automatically collects all that data and puts it in a giant database that anybody can access. So you can go online, look at any point in the sky, any wavelength, any depth, and you will get all the images that are collected there. It's a huge, massive collaboration. There's thousands of people involved. it has a huge impact. Like every year, thousands of papers come out based on the data of this telescope alone, and it's grown into a worldwide organization with telescopes all over the world, continuously collecting information about the universe. It even spreads towards citizen science. There were, for instance, one famous story is there was a Dutch school teacher, Henny from Arkel, who was looking at some images of this telescope and discovered a new type of galaxy. So these were totally citizen scientists that looked at the data. So what this shows you is that by making this data easily available and well organized and easy to access, you can massively improve science. This is one example of networked science. Networked science means it's science on a global scale where everything is networked, where we take all our data, put it in online tools where anybody can access it. And this allows massively new discoveries. There's a nice book by Michael Nielsen that explains all these discoveries. And the reason why we make discoveries faster is something he calls the science serendipity. It means making accidental discoveries more likely by making data and IDs available to lots of people, so that you by chance there's some person who's looking at this data and has a new ID, or makes a new discovery, or can help you solve a problem that you were having. Right? So if all these people are working in the same platform, that means that all the power, the brain power of all these people is available, and you can make new connections and make new discoveries. It's incredibly important for science, because science is an infinite game. It's not a game that changes, that has a finish line next year. It's basically infinite. So if you want to do it well, we should have just causes. For instance, exploring the universe or understanding how learning works. Build trust with people to collaborate and be flexible in going into new directions. But if you look at different sciences trying this, you find that this only really scales if you remove all the friction from the system. Right? If people have to spend too much time getting code or finding data or having to spend days trying to build a good model, people won't do it. Right? So if you make it really easy, if you have common formats, if you have clear guidelines, if people can do things in seconds, then you have a massive amount of people that can do it. There's only a few amount of people who can spend days doing something, right? So if you make the system so that it's very easy to do stuff and to share stuff, then you massively increase the impact of whatever you're doing. And finally, give credit when credit is due. Right? People won't stay in the system. You won't build trust if you don't give people proper credit for their work. If you want to know more, there's an excellent book by Michael Nielsen called Reinventing Discovery, which I very much recommend you to read. So at OpenML, the question that we want to answer is, can we realize network machine learning? Can we pool our resources and our knowledge to really understand how learning works? Can we build new machine learning AI systems and really understand what's happening? And this is an excellent question because, well, machine learning is not an easy process, right? It's a very complicated process with many different actors or tools. For instance, going from the raw data, there are a specific group of people, data engineers, that know how to handle the data, how to reprocess it. Other people are very good at building models. Other people are very good at deploying models and putting it into real life. And of course, some people can do all these things, but typically the way machine learning works is that different people do these things very well. And then there's also closing the loop. After you deployed your machine learning system, you discover that it doesn't work as expected. So you need to improve the data. And this is a continuous cycle. This is currently a very hot topic called data-centric AI. How do I improve my data to get better models rather than just change the models given the data set? Right. And there's a huge amount of tools that you have to learn to do this. So this means that it requires a significant amount of expertise. There's knowledge that is very tested, hard to access. There's not like one book of this is how machine learning works, right? It requires a lot of experience, and all this knowledge and information is currently very scattered over thousands and thousands of papers. Nobody can keep track. It's often very unorganized. Often hard to find the right data or code. Although it's not bad. It's not machine learning is in a pretty good state because our code is typically quite easily available. But a lot of the implicit knowledge that goes into machine learning is hard to access still. And all these questions that you want to answer, like how to parse data, how to choose a model, how to reproduce or reuse a model, that's all very specific information that we have a hard time getting access to. So the question you want to answer is, can we organize all of our results? If we could get all this exhaust, all this amount of all these results that come out every day on a massive scale and organize them, so we can really learn what works, what doesn't work, and how to build systems. So what if we could organize all the world's machine learning information and really make it universally accessible and useful? And with a nod to our robotic telescope, could we actually automate systematic collection of machine learning experiments? Right? We may be able to build tools called automatic machine learning tools that automatically collect massive amounts of machine learning experiments, organize them online so you can easily get access to them, and really build better systems, learn how to do stuff, answer all kinds of questions with just a few lines of code or a few searches on a website, instead of having to do all your experiments from scratch. Okay. So that means we have to organize all information. That means that for every data set, we want to be able to find all the models built. Currently, we can quite easily find data sets online. And there's an interesting initiative from the NERPS conference. There's now a dataset track. So there's very interesting new data sets coming out. And what's often missing is, okay, you can find a data set, but it's hard to find all the models that people built on it. Right? So if you build a system like this, it should be easy for every data set to see exactly which models people built on it and how well they perform, and which tools, which algorithms that they use to build those models. For every model, every experiment done, which exact data set did they use, which exact algorithm they use, which settings, which neural architectures did they use to build that model. And then for every algorithm or every model, find how useful it is for every data set. Right? You may ask questions like, okay, I have this particular kind of algorithm. What cases does it work well on, and when does it not work well? Right? We also want to answer those kind of questions. So, because we want to build reproducibility and trust, we need to really think about how we do this. Right? So, for every data set, we want to make sure that there is rich and especially correct metadata attached to it. Right? So that means we will automatically extract a lot of metadata from the data sets that we have. That makes it easy to search for specific kind of data sets, and also makes it helps us to know how to use those data sets. We should check that the data is correct, that the metadata is correct, that the feature types that we have are correct. And well, in the course of OpenML, we've had many interesting stories about some data sets which were incorrectly labeled or something like that, and which led to massive problems. For instance, there's one data set called liver disorders. And the people who created the data set added a column called class. And people just thought that the class is the thing they had to predict. Turns out that that feature class just sets which instances were in the training set and which were in the test set. So that means that thousands of papers were basically trying to predict random distributions, right? So having that metadata correct is very important to build trust. Is a task that you want to solve clearly identified? And can we also easily automatically import any data set? Like before, if I have to spend a day trying to import data sets, I will quickly stop. And I won't be able to do experiments over thousands of experiments because I don't live that long, right? So if we can organize all that data so that all the data is uniformly formatted, I can write a script and run it over thousands of data sets in one go, right? So we definitely make sure that all the data sets are uniformly accessible. This simple, that's one line of code to get a data set, and no matter which one, you will get it in specific formats. Secondly, also for the model, we want to know the exact data set and algorithms used. We want to be able to trust the models that are there. So we want to have exact metadata, like the versions of the code, dependencies that are in the code. the exact configurations, like which hyperparameters that you use to build a model. You want systematic evaluations. If you have two evaluations of models on the same data set, you want them to be comparable, right? So you want to have the same trained test sets. You want to have the same metrics and the same implementations. And it should be very easy to reproduce. If I find a model online and tells me it has 98% accuracy, then I want to be able to reproduce it easily. So the question is, okay, this is a good idea, but okay, so how do you collect all that metadata? That's not so easy. And can we automate that? Because nobody in the world will manually annotate all this information, right? So we need to do this in an automatic way. So what we collect in OpenML are, first of all, data sets. For every data sets, we keep all kinds of metadata like size, dimensions, number of missing values, feature types, and so on. Where does data come from, different data versions, and so on. Then we define the tasks, the problems that we want to solve, like classification, regression, what to learn, how to evaluate. Do you want to evaluate this with RRC or accuracy or something else? For every algorithm, we call that a flow. That can be like a machine learning pipeline or neural network, which are the dependencies, which code was used, and so on. And then for runs, every model you built, every experiment you run, how well did it work, which configurations did you use, and so on. So we want to collect all this data automatically. And we basically do that through APIs and integrations. So instead of building a platform and requiring you to go on the website, upload a data set, and then fill out lots of manual metadata fields, that will never work. So what we do instead is we build integrations into the tools that people already use. For instance, if you use Pandas or R, we build integrations into these tools that automatically do the annotation for you. Right? So no matter whether your code is loaded into a notebook or a Colla or your local application or a script, we provide an API that can then upload the data set to OpenML, and in the process also automatically extracts all the metadata. Same with pipelines. If you build a model, it automatically collects exactly what the model looks like, what are the dependencies. If you share a model, it automatically uploads evaluations. It also evaluates on the platform itself, by the way. But it makes sure that all the information is there and uploaded automatically from the tools that you already use, right? So if you use scikit-learn or MLR or TensorFlow or PyTorch, we have integrations that make sure that all the information is extracted automatically and uploaded to the platform. Right? Okay, and then from there, you can then explore all the data through a website. We have a website, I'll come back to that. But you can also easily import all of that through our APIs. We have APIs in different languages. So you can access all the data anybody has ever put on the platform. So we have different integrations into different tools like Pandas, scikit-learn, TensorFlow, R, and so on. So if you have a Pandas data frame, you can export that to OpenML. If you have a model in scikit-learn, you can export that to OpenML. If you have a model built in TensorFlow, you can export that to OpenML. And then later, if you find, okay, I find an interesting data set, you can download the data set directly into Pandas data frame. Or if you have a model, you can directly instantiate that in scikit-learn and TensorFlow. Right? So that makes it really flexible. You don't have to worry about how data is formatted in any way or how the metadata is collected. Through these integrations, you can just act like this is a data set and you directly get the data in the data frame that you want. And you can use to build models with it. I'll show some examples in a minute. And so what this allows you to do is truly frictionless machine learning, right? I can have one person who says, okay, I have a new data set, and now publish it to OpenML. Somebody else can say, okay, I want to download the data set, I'll build a model on it, and then share the model back on the platform. And so you can have many people all over the world collaborating, some creating data, some building models, some downloading models and building other models based on that, or doing all kinds of crazy things with all this information. It's all open, it's all open APIs, open source. We have a GUI, a website where you can also explore all this information. So we are currently transitioning to a new website. So if you go to OpenML right now, you have the old website. This is the new one. And maybe it's easier if I just very briefly show you how that works. All right. So yeah, you can access it. It's on new.openml.org, but it's not ready yet. But you can, if you want, you can play around with it. So that's our website. So you can browse all the different data sets that are on the platform. So you can look at all the data sets. You can see what they are about. So you can go through all of these. To say, well, maybe an interesting one is cover type. So this is about the cover type of trees. And I'm just, oh. I'm sorry. This is very dangerous to do this, given that it's still in beta. I'm not sure what happened. Let me just start over, sorry. Cool. So what I can do, so there's of course the description and so on, lots of information about that. There's detailed information about the features and so on, amount of missing values and so on. It's all machine readable. You can, there's an automatic analysis of all these things. So you can, for instance, look at the distributions of all the features. You can look at the distribution of, in this case, the target classes that are involved. This here show, oh, sorry, distribution of the targets classes, distribution of the most important features. There's a feature importance ranking to see which features play a role in the predictions. There's feature interactions and so on. And like I said, this is a completely open website, completely open format. So if you think, oh, it would be nice to add another kind of analysis for the data set, you can do that, right? So this is all Python based. So if you want to make new visualizations, you can definitely do that. Very happy if you want to do that too. Another thing that may be interesting to show you are collections. So for instance, we have benchmarks. So when people want to evaluate machine learning algorithms, it's interesting to have a good set of benchmarks to test these algorithms on. So we put quite a bit of work into that as well. And so, for instance, this is one of our benchmarks. Oops. And so these allow you to basically test your algorithms on collections of data sets that we have created beforehand using a few lines of code. So if you want to test your algorithm, you just write a code like, give me all the data sets of the benchmark, you get trained test splits, you can evaluate your models, and this is done automatically for you. Right? This makes it really easy to test benchmarks on a large scale. I can, for instance, show you one. This is for HTML tools. This compares different automatic machine learning algorithms on a bunch of data sets, problems. And when you do experiments and you upload the results back to the platform, you can also analyze all the results directly. It's a bit slow still. Need to speed this up. Yeah, you will definitely be able to get an overview of the different algorithms that were performed and how well they did. Of course, it's slow to give a demo. Okay. Okay, that's a pity. Yeah. Okay, but yeah. So all the data, all the experiments, they're all accessible to the website, and yeah, feel free to look around. I'll go back to my other presentation. time. So these are some examples of the API. And like I said, it's very easy to run experiments. So in this case, I use scikit-learn. I have this one line of code which downloads a certain task from OpenML. And this includes trained test splits, evaluation metrics, everything. It's all machine readable. You can build any model you want. In this case, I have a simple random forest classifier. And then this line of code just runs the classifier on the task. It automatically creates trained test splits, trains on tests, evaluates on the test sets, trains on train sets, tests on test sets. Does all this stuff for you. And then also, if you want to, you can publish these runs directly to the platform again. Same for TensorFlow. In this case, I build a neural network. And again, I can then train the network on any machine learning data set. And it's really, you don't have to worry about downloading data sets and reformatting them. This is done automatically for you. Right? So you can train a model on any data set by just replacing the ID of the data set. Basically. Same in R, it's exactly the same interface. You download the task, you run a model on a task, and you're done, basically. So that makes it very easy to collaborate. Anybody can share data, anybody can import data, anybody can design algorithms, share models, and so on. So it really creates a very flexible collaboration system. We have a quite large community over the years. So we have over 250,000 yearly users who use the website, who use our API. We have 30,000 people who are registered, so they can also upload stuff. So OpenML is free to use entirely, so you don't need to register. You can download everything for free. You only need to register to upload things to the platform. It's used in over 700 machine learning publications, and we currently have about 20,000 data sets, 8,000 flows, and 10 million runs. And so one example of design serendipity is automatic machine learning. So when OpenML was gathering experiments, people started using this information that's on the platform to make informed decisions about how to build models. Right? So there are a number of automatic machine learning tools like scikit-learn, there's AutoKeras, and so on. And they use smart optimization techniques to build the best models, best pipelines, or best neural nets. But if you have access to this cloud of information, you can actually use that to make smarter decisions. Right? And so increasingly more and more of these automated machine learning tools have been using OpenML to download information to make the right decisions on how to build the best models. So one example is scikit-learn. So what it does, when you give the data sets, it looks at OpenML, okay, which data sets are similar to the one that you're giving me. And if I have a similar data set, then I can start with pipelines that worked well on that similar data set, right? And I can try those first. And the paper shows this massively improves performance of the AutoML technique. Amazon did something simpler. So they have it's a quite complicated system, but basically what it does, it learns how to tune the hyperparameters of your machine learning models. And then they trained that model, which is based on neural net and Gaussian processes. They trained that by using over 8 million experiments from OpenML. And then this model predicts basically which hyperparameters, which settings are best for the particular data set that you give it. Similar work has been done by Microsoft in their technique to recommend pipelines. We have our own techniques as well that we develop and also make use of all the information. And so it has been really interesting to see how the AutoML community has made use of all the information that we have online and use that to really make machine learning easier for lots of people, right? So now not only do you have good tools to automatically build models, but these models also make use of all the information that's online. And so the more data we share and through OpenML, share and organize through OpenML, the better these tools get. So we're building an increasing amount of knowledge about how to build machine learning systems. We also have our own bots, like I said. If you upload a data set to OpenML, at some point, one of these bots will try to build models automatically on a new data set. Right? So this systematically explores the whole space of different machine learning models, and it shares the results back in OpenML. Right? So this makes sure that we get a lot of information. Like this bot alone built over 5 million experiments, models basically. And it's also interesting to see how this relates to humans. So this was a one data set in OpenML, and so you can see over time. So these were all people building models, and this is performance, AUC versus time. And so in the beginning, mainly people were building models on this data set. And then in orange are the models built by the HML tools. And so I think these ones were still not looking at the previous results. Today, they just built models by themselves, and they get performance pretty close to the humans. But we also have HML tools that look at what humans did and try to improve over that. Right? So we can have all these humans and these bots in the same system. And yeah, hopefully this will be more turned around in the future. So the HML tools build models first, and then the humans trying to improve over them. So OpenML is an open science community. We do regular hackathons. It's a bit slow with COVID. We do some virtual hackathons, but hopefully after COVID is passed, we'll have a lot more in-person interactions again. We have a great bunch of people from all over the world. We have a community, and that's really a community. So we have contributors, we have core contributors. Anybody who contributes also gets rewarded by that. We have rules about how things work. We also have a foundation. So if your organization wants to partner with us, that's also possible. And we even have a small company. So if you want to do projects, that's a possibility. All right, thank you for your attention. I just want to close by thanking the whole OpenML team with many bright people from all over the world. Thanks.
Thank you, Joaquin. Thank you very much for the very interesting talk. And I think that we can proceed with questions, and we are going to alternate questions from people who are in the room and questions from people who are online. So maybe let me start with the first question. So one of the first question is about if you store a copy of the data set, and if there are problems with the size of this data set so that you need external storage.
There are two ways of storing models. So you can either store by reference. And in that case, we can't always guarantee that it's easy to load them, right? Because they may be like something like ImageNet requires a lot of processing. So there we have to resort to data loaders. But for most of them, like up to several gigabytes, we can easily store them. And yes, we do store copies. We store them in a compressed format that's based on Parquet. So it is quite efficient. So we can store quite large data sets. I think we have data sets up to 8-9 gigabytes. But I think we haven't really explored how far we can go yet. In principle, there's no real limits. But yeah, I hope that answers the question. But yeah, there are cases where data sets cannot be processed. And in that case, we have to resort more to data loaders and so on.
So we also have a question here in the room, and also just as information, if you have questions in the room, please come to the microphones and to Felix.
Hi, Joaquin. So thanks for the nice talk and the impressive system. So as database people, at least I'm very interested in the data aspect of it. And so I would like to hear your take on the problem of data preparation, data transformation, right? So everybody fiddles around with the data a little bit, transforms some units, or writes in their paper, I removed all lines where this value had 0, and so no data set is really alike, right? So how do you deal with this in the system?
So in the base OpenML system, we have versions of data sets. And for every version, we have all the metadata, right? So you can compare two versions. And you can see if this version was like not clean and this version was clean, like they imputed missing values, or so you can sort of automatically detect that. For the HML tools, this is more documented. So in that case, there's a pipeline of steps, and then you can see the entire pipeline, like everything, like scaling, musical imputation, feature selection. You can see every step that has been done to arrive at a certain model. Right? So there's two ways. So either it's automated and then you have the pipeline, or it's just random, and then you can still compare two versions of the data set if you want to.
So maybe it's up to us then to also prepare these, have these pipelines for the data transformations and document them just like you do for the models.
Yeah, totally. And like I said, it's an open system, right?
Yeah.
So if you have a good pipeline and you want to run that on all the data sets, that will just take you an hour. Okay. So you can do that, yeah.
Okay, thanks.
Awesome, thanks.
So Angela,
Let's
do you have more
proceed.
questions?
Yes, yes, I have more questions. So Nessim Tatboul asks about updates. So in fact, in our community, we are very interested in how to update the data. Is the version control system, which is part of AutoML, in which you can actually handle data set versions or their provenance, their lineage, and so on.
That's a very good question. It's something we have struggled for a long time. So we've done lots of experiments. So one big point was about a year ago when we were moving from an old text-based format, basically CSV, to something more modern, like a binary format like Parquet. And with CSV, you can do pretty good version control because it's all text. You can, like, individual changes, you can div them. But with binary formats, you don't have that. So in the end, we did decide to go for binary formats because otherwise, like loading large data sets was not possible. So we need binary formats for large data sets. Yeah, so in that case, it's harder to really do versioning. But so the versioning is very simple in this case. It's just a new version based on an old version, and that's basically the information we have. Yeah.
So we have one more question in the room. Sorry.
We do have a small experiment, DataGit. I think it's data.github.com. And so GitLab.com. So there we have an experiment there, and so you do versioning basically on CVS and on CSV data sets, but it's not what we use in production.
Thank you, Joaquin.
Thank you, Gary.
Yeah, thanks for the nice talk. I was wondering, how do you ensure on the quality of not only data sets, but the executions and the models that are created from the data set? Because, I mean, you're offering a website where everyone can create an analysis and publish it. So there might be interesting statements coming from these analyses. So how do you monitor this?
Let me see if I can share my screen again. Okay. This is, for instance, the result I had before. So in this view, we have the colors here are different algorithms, different models, and the rows here are data sets. So these are all data sets. And then basically you can see which are the best models for every data set. So we don't really filter beforehand, but afterwards, you can easily see which are the best models for your particular data set of interest. And you can do all kinds of analysis, like give me the best models for every data set, for instance. That, like what the outside learn guys did was exactly this. So for every data set of ML, they said, okay, store the 10 best pipelines. And then they use them for to make predictions. So yeah, short answer is basically that we don't filter it beforehand, but you can filter afterwards which data sets you find interesting.
Okay, maybe to extend on it, moving away from metrics and moving towards something like, okay, I have these two data sets, I'm combining them in a way that might create a result that may be able to be deducted from the data set, but not necessarily from a reasoning, from a logical reasoning.
Right. Okay. Yeah. Just to follow up, this is so every task you can get an overview like this. So you can see exactly which are the best models. Your question was, okay, which are really valuable insights basically compared to like a good model but bad predictions.
Yeah, essentially valuable insights in a.
Yeah. So that's something we haven't tackled yet. Something we are setting up currently is for every data set, we want to have discussion boards where people can discuss, hey, this is a good model and this model looks good, but it's not really. So you already can like models and so on, but that's not very interesting. But in the end, we want to have basically discussion boards for every data sets where people can come together and voice their opinions on what's useful or not. Because this is something we cannot really solve in a scalable way. This really requires people to share their insights. Yeah.
Thanks.
Does that answer your question?
Yeah, thanks.
Okay. If not, let me know.
So Angela, more questions from the chat?
Yes, there was another question by Ghislaine Fournier. Since you use Parquet, do you support heterogeneous data sets? So basically you don't support, is it true that you don't support heterogeneous data sets, for instance, in JSON? Or do you have mappings mechanisms to allow that?
Short answer is no. So if it's entirely heterogeneous, we don't support it. And that's just a decision we had to make at some point. So what can you support? What can't you support? The more, if you allow any point of data set, you can have more data sets on the platform, but you can do less with them. So at some point we decide how to do this, and we basically decided that the interface is going to be the data frame, because that's how most machine learning algorithms work. They have like a pandas data frame or an R data frame, and that's the way we communicate. So if you have a heterogeneous data set and you can import it into a data frame, no matter how you do that, you can share the data frame, right? So you can share like organized information about that. Yeah, that's a short answer. So if you have models that work directly on heterogeneous data sets, we don't support that. But if you even like graph models, they first built an adjacency graph or something like that, right? So for most of the cases, there's typically this intermediate format that's a data frame, and that's the interface we're working on basically.
So there are no more questions here in the room. Any other questions? Otherwise, I think we would have probably should slowly move on towards the next presentation. Or is there one more question, Angela, that maybe can answer quickly?
I have one last question for Joaquin. So you were describing this mechanism by which you identify similar data sets. Can you elaborate on that? So how do you define similarities among data sets? So you use features, you know, which kind of similarity functions?
This is actually a very hot topic in machine learning right now. So what we had before is basically we build a vector representation of the data set. And that's basically, that's based on all kinds of statistical information, theoretical features. So we look at the distribution of the data set. We extract all kinds of statistics about the distribution. That's transformed into a large vector, which is like 130 values. And then you just do cosine similarities, something like that to do that. That works nice for tabular data. If you go to image data, that doesn't work so much anymore. So in that case, there are techniques like optimal transport that do that well. What they do, they typically take, if you have two data sets, they take a subsample of points from both, and they look basically how geometrically similar they are to each other. There are other methods where you build a neural network to predict similarity. Or you look at you take a battery of models, you train the models on all the data sets, and if a battery of models has the same relative performance on two data sets, that means the data sets have internally some kind of similarity. And that's another way to do this. So it's an unanswered question, but it's one where we have quite a few interesting results, and we hope to put all of that online in OpenML, so you can basically have a list of similar data sets. Yeah.
Very interesting. Thank you. Thank you very much, Joaquin, for your talk and the enriching Q&A session. Yeah.
Yes,
thank you for having me.
Yes, thank you very much, Joaquin, indeed. And